Okay. Let's kick off class by, when do you want to do your exam? I know the syllabus says next Wednesday, but that's when I was confused and we had lab on Wednesday. Now it's on Monday. So it has to be so it should be next week because that's like perfect break in the semester. So you can either do it Monday during lab, right? So you have the 2 hour and 50 minutes. So that would be at 8 a.m. I don't think we could do the afternoon lab session. Just because there's a lot more people in person that are doing the live lab session in the morning and are actually on campus. The folks who do the afternoon, I think there's 8 or so people. And I mean, I have a lot of people there live, but some people aren't necessarily live. So unless the 12 or so people in the morning session can go to the 1 o'clock session, which I doubt, right? Anybody here who's in the money lab can't do the 1 o'clock session? Yeah, so that's the problem. So it's either going to be Monday morning at 8, and there's a few people who can't do it in the 1 o'clock lab that I can help. I can deal with those independently, or we do it during class on Tuesday or Thursday, which means you get 1 hour and 15 minutes. That's just the time we got, right? That's when the class starts and ends. I mean, I can start class a couple minutes early, but not too much earlier, because if you have a class before this, it wouldn't necessarily be fair to them to start super early. So
yeah, Monday morning.
have one vote for Monday morning at 8. 2 votes. What's that, Avery? It'd be 1 hour and 15. I mean, we don't have a lot of options, right? So I know it's not ideal, but that's just the circumstance that we have, right?
All
right, so let's do a vote. Let's see who wants to do Monday 8 to 11 a.m. Okay, how about in TV land? Any vote? If you give me a thumbs up in the chat, I can see that way. No thumbs up on your screen. All right, how about Tuesday during class? Any votes? 1, 2. Anybody in TV land?
Oh, would it be the same exam?
It probably, maybe I would take out 1 part or 2 parts of a question, but it would be mostly the same parts, same constant. So I might try, if there's 4 parts for a question, I might cut out 1 of the parts. Yes.
Paul, my only concern about doing it in a 1 hour and 15-minute time span
Yeah.
versus the 3 hour is because a lot of people, at least I know I have, and what I hear of a few others, it took about 2 hours or more on the previous test. That's the only concern that I have about doing it in that short time span.
Yeah, I mean, I write the exam, so if you work diligently, you should be able to get it done in 1 hour and 15, 20 minutes. I know you take 2 hours, right? Partly because you have plenty of time. So if you had more of a time crunch, you might work a little bit more efficiently, maybe. I'm not saying definitively, but I think most people did take 2 hours or so, but that's because you knew you had 3 hours to take the test. If you know you only had 1 hour and 15 minutes, it's not like you look down at your clock and said, oh, I've only got 1 hour and 15 minutes. I better, move these problems along. You might tackle the test differently, is I guess what I'm suggesting, if you know the time. So yes, sir. People ask. Monday we come back from break. We can't move it out a week. There are too many other things happening. There's also, and the other thing too, is you have a lot of students in this class also taking another class with me. And so I'm trying to make it, even Steven for them. So we would have a test 1 week in one class and a test another week in the other class. So what say you? Tuesday? Any Tuesday votes?
Was it unreasonable to do the Monday afternoon period? Is that not gonna happen?
There are too many conflicts. A number of people raise their hand. How many people can't do Monday afternoon? Can't. So raise your hand.
Yeah, I've joined that.
So I'm looking and I see 7 hands raised.
Okay,
Yeah, I've got other class commitments. So the other option is Thursday during class. You prefer Thursday during class? 3. Anybody in TV land? 4.
I think Thursday's good. Yeah.
It's 5. So right now it's either Monday or Thursday. Amber 6. All right, so let's do it this way. I'll do it. So I'll do a new poll. So it'll be Monday at 8. Yes, it would be the week from we get back from break. Oops. Okay, and let's launch it. All right, so please vote. And then let's do it again in class. So who says Monday at 8? Keep your hand up high so I can see. Okay. So who says Thursday? Okay. It looks like the Thursday's won. Because it's 6 plus 3 is 9. Actually, it's tied. So has everybody voted online? Because it just changed. Okay, could you make Thursday? So if you did Thursday, that would be lean towards Thursday, so.
I will for a long time.
All right, I guess you guys break the tie, so it's gonna be Thursday during class. All right, thank you for voting. So we'll have that next exam. 2 weeks from this coming Thursday. It'll cover everything up to including what we do today. Yes, sir.
So we're gonna do lab Monday.
We'll do a lab when we get back. No, I won't give you a lab that Monday just because the deal normally is I give you the week to focus on studying. So we'll do no lab on Monday. That way you can have extra time to study because a break, unless you want lab. I mean, I have a lab ready to go. Who would like a lab on Monday? You?
That's
Anybody?
a good joke, but I think I'm good.
Okay. I think you guys are gonna lose, so. All right. So it's only 2, so, all right. So we will do Thursday, so 2 weeks from Thursday during this class. You're allowed 8.5 by 11 sheet. I will post the exam review session. We'll do that on the Tuesday before. I will post it when I get back to my office, as long as I remember. I'll post it. So for those of you who want to take advantage of the break to study, you're welcome to. Just encourage you to do that, because again, when you get back, you're going to be a little snoozy, and especially if you haven't done anything. So something to think about. Caden, yes, sir.
Not a class after all, you can go over them.
The answer is unfortunately, unless everybody can do that. So I would love to do that if everybody in the class said, I can do that. But if one person says no, it has to be fair for everybody.
What's the question again?
Can we have extra time if they don't have a class after this? I know this classroom is being used after our exam. So it would probably be beforehand. But again, if you have a class at 9:30, I can't make it fair. So I'll probably show up 10 minutes early to give you closer, and maybe we can go 5 minutes late. So maybe we can get a full hour and 30. But that's probably all that we can do. So,
A lot,
yes,
a lot of us have John's 350 class that doesn't meet on Thursday.
yeah, but it's not just you. There's a lot of different people in this class. So we have a bunch of ECE students who might have other commitments. And again, we can't do it after, because in this classroom, there's a class that comes in after this classroom that uses this classroom. So even if I got another classroom, it would just be, everybody would have to agree. So it's probably not going to work. Like if I ask now, is anybody busy from 9:30 to 10:45? Yeah, see, so, and again, this is not calling people out. That's just what makes it fair. So we'll say 9:20 to, I'm sorry, 10:50 to 12:20 or so. We'll do it on Thursday. Okay. All right. So thank you for agreeing to that. Let's get into synchronous motors. So again, you don't commonly find synchronous motors, but I've actually been seeing more of them recently. Like I said, I'm still sort of helping out on necessary in a project in New Hampshire. But they are basically just a synchronous generator. So it operates exactly the same. The only concept is that the power is going in. So you have some mechanical load on the system, and the mechanical load could be just getting this thing to rotate, right? You have friction and windage losses. So you're going to have losses, and that's what you have to account for. So the mechanical load can be just friction and windage losses, but because you have this generator or this motor that is capable of importing or exporting a lot of reactive power, then it works perfectly fine. So if you're a synchronous motor in an application where you're actually driving a load, so you're connected to a conveyor or something, you're talking synchronous motors from 200 horsepower, maybe to 20,000 horsepower. All right. The one that I've worked on is 25 MVA. I think it can import, and export. I think it can export 50 MVA. So if you do the conversion, right, it's much bigger than 15 megawatts. But that's a very unique case, because again, that whole synchronous machine, its only purpose is not to drive any load. It's just there to be able to increase the voltage or decrease the voltage depending on the circumstances of the grid. You talk about it in heavy industry, so pulp and paper mills would be really good. As long as you have a constant speed application, then it makes sense to go with a synchronous motor or a synchronous machine. The problem with them, though, is that constant speed thing makes them more difficult, because actually having the ability to have variable speed or not have to operate at a specific speed sometimes can be a good thing. One of the other difficulties, too, with a synchronous motor is starting the synchronous motor, and we'll talk about that when we get to startup of a machine. So everything is the same. How it operates, get this out of the way. You have a field current, so you have to provide it with a field current, and every synchronous machine that I have seen always has a field current applied to it, so you can monkey with the voltage. That gives you that steady state, non-varying magnetic field. It gives you a constant north and south. You apply, so you energize your three-phase motor. So in the case of a three-phase generator, we're getting this thing to rotate, and then that's inducing a current in those stationary windings because you have a magnetic field that's changing. In this case, we're the opposite. We've got a current flow that's going in, and that current flow causes a rotational magnetic field. And then that magnetic field that's on the rotor is going to go ahead and cause those two to chase. And so that's where you get the magnetic field. So this concept right here, this three-phase set of current produces a uniform rotating magnetic field. That's all the work that we calculated at 1.5 V sub m that we did in chapter 4. That's the material that we looked at for that. So they will either line up or they will repel each other depending on what we're doing. And the rotor magnetic field is always chasing and trying to catch up. They never will catch up to each other. Why is that a bad thing that they will never catch up to each other? Or why is it a good thing? Can the magnetic fields ever be perfectly aligned? Yeah, the answer is no, because the only way you output torque is, remember that torque angle delta? So you have to have a difference in angle between EA and VT, which is consequently the same angle that you're going to get from the magnetic fields. And so that's the only way you can output any torque. So that's why the larger the angle, the greater the delta, the greater the amount of torque, mechanical torque that machine provides. So what is the equivalent circuit? It's exactly the same as a synchronous generator. The only difference is the direction of current is going into the machine as opposed to out of the machine. And you can draw a phasor diagram really well. Phasor diagrams represent the information, and that's when we talk about this whole concept of, whoops, why isn't this? I swear I don't know if it's my pencil or just my luck, but this is working fine and it's intermittent. So now we look at EF relative to VT. So our terminal voltage is almost always going to be lined up with our x-axis. And then we look and see if EA is leading or lagging our VT. If it's leading, then it operates as a synchronous generator. If it's lagging, it's operating as a synchronous motor. The direction of motion, that's just determined by how you connect those stator windings. So just like we had when we did our calculation, when we swapped any two phases, you can do the same thing for a synchronous machine. You just swap the two phases, the magnetic field will reverse direction, and you get reverse operation. So here are some synchronous diagrams, and you can see this is a synchronous motor or operating as a synchronous motor because look at my torque angle, delta. It's negative. VT is ahead of EF. So this is operating as a synchronous motor. The torque angle between these two is exactly the torque angle as between my rotor and my net magnetic field. Where do I get my net magnetic field? B net is equal to B rotor plus V stator. So this vector right here is B sub S. And my net magnetic field is dragging along the rotor. So that's another thing that indicates that this is a motor, because in the case of a generator, our net magnetic field was behind our rotor field. So our rotor was inducing currents in the field. Where this is inducing a magnetic field that's pulling the rotor magnetic field along. So this is a case. So this is a phasor diagram. So kind of an extension over here. And this is a phasor diagram showing an under or overexcited machine, or can you tell? I'll give you a hint. The answer is yes, you can tell. What's the key? What about it? It's pointing down? Well, that just tells us it's a motor, right? Because if you remember, this is EF, this is X sub S, and The current is going into a motor, right? So when I subtract the voltage, because it's KVL, so or EF equals VT minus the voltage drop across X sub S. That's going to be a negative number, right? But why is this an underexcited machine? Remember the magnitudes? The magnitude of the terminal voltage is greater than the magnitude of the magnetic field of the EF, which implies that the reactive power that's going to be consumed by that inductor is being supplied by the grid. I don't need to make EF so big so that I can send reactive power and support the grid or support my own machine requirements. So this is a case where I have underexcited machine. Now the question is that a leading or a lagging power factor? Or can you tell? Lagging power factor? Let's take a look. We know, here's my terminal voltage. Here's my current for it to be lagging. Then I do my S equals VI conjugate. So I get that, right? When I just run it through that. That means that P and Q are both positive. In the case of a motor, which is the current direction? In or out? In. Why is the current direction in? Because the power is in, right? That dictates. And if P is positive and going in, what's the direction of Q? In or out? They're both positive. They're both going in the same direction. So Q is going into the machine. So that is for the lagging power factor. We have an underexcited machine. If it's a leading power factor, then we end up with a different result. And actually, this is a typo. I put lagging, and I said, oh yeah, no, this is correct. Sorry. I just looked at it too quickly. So that is correct. So that lagging power factor means your VT magnitude is going to be greater than your EF. So when do you apply them? Because you want to be able to provide a lot of reactive power. It doesn't make sense to put a small motor out there because you're not going to do much for supplying your reactive power. If it's going to be a small application, then just put a cap bank on. Just put a capacitor bank and it fixes all your problems. And how do you control the power factor? You just adjust excitation. We saw that if EF was less than VT, then we were operating underexcited with a lagging power factor. How do you make it leading? You just put more field current in the machine, and that's going to increase the magnitude of EF, and you're going to end up having an overexcited or a leading power factor. They operate at a high efficiency, higher than an induction machine. And that's partially because the rotor circuit is more efficient, but we'll get into more of that when we actually study or actually go ahead and do more details about induction machines. And the good or the bad is that they operate at a constant speed. So the other thing that's interesting, if we're running at low power, 500 RPM or less, and fairly high power requirements, your synchronous motor is actually cheaper to make than an induction motor. Okay. So if you can handle constant speed and also starting them, they work really well. So here's some advantages: reciprocating pumps, if you need a constant speed, compressors, if you need a constant speed, crushers, rolling mills, pulp grinders, etc. Now, most of the time, though, when you buy compressors and pumps, they will be driven by an induction machine, not a synchronous machine. Anybody want to guess as to why? Here's the slide. I skipped ahead a little bit, but that's okay. The real downside of a synchronous machine is starting it. Because remember, a synchronous machine wants to operate at synchronous speed. It only wants to spin at synchronous speed. So if you energize a synchronous motor across the line, it as quickly as possible goes to whatever its synchronous speed is. So if it's an 1800 RPM machine, the moment you flip the switch to energize it, it tries to get to 1800 RPM, which can damage the unit. It's very difficult to do that. So how do you start a synchronous machine? You don't start it across the line. There's a couple different ways you can do it. How about a variable frequency drive? If it goes to synchronous speed, that's perfect, especially if your synchronous speed is not at 60 hertz, but at 1 hertz or 1/10 of a hertz. Instead of running at 1800 RPM at 60 hertz, at 1 hertz, it's 180 RPM or 18 RPM. That's not a big deal to go ahead and do it. So if you were to go down to Maine Independence Station, which is just down the road here, they have GE gas turbines, and a gas turbine has a synchronous generator connected to it. Well, how would you start a gas turbine? You light the gas and you let it spin up to go up to speed. You can't do that because the gas in and of itself, if it just goes upon and hits onto a blade, if that heat goes onto that blade for a long period of time, the blade can't handle the constant barrage of natural gas. And so it would melt or warp. And so you can't just flip the switch on a gas turbine, on big gas turbines, and get them to start. You actually have to get them rotating. And these are big units. So how do you get them rotating? I've got a synchronous machine connected to it, right? It's called a big synchronous generator. Why not go ahead and use that to get it to spin? So they use a variable frequency drive. It's actually called a load commutating inverter that takes power from the grid at whatever voltage it is, and then converts that to DC and then back to AC at a much lower frequency. And those VFDs are rated for like 15 MVA. To get that turbine moving takes a lot. So GE uses the concept of a variable frequency drive to start it. The one that I worked on in Texas, they use an external prime mover. They use something called a pony motor. A pony motor is just a little motor that is somehow mechanically coupled to the shaft, and you get that thing spinning. And then over time, it gets the generator, or the motor, I should say, to be spinning fast enough that when you can hit the field. So the project that I worked at Houston, that one actually had a 1,000 horsepower motor that would be able to get that synchronous machine, because that had, again, it had a gas turbine on it. And so you couldn't just go ahead and light it off. You actually had to run it for a motor for maybe an hour or two to actually get it up to speed. The other thing that's interesting about that is, so let's see. Not that one. Let me do over here. So I will apologize in advance, but you'll have to see a lot of information here in a second. All right, so let me get rid of some of these marks. So remember that pumped hydro storage facility that is in Western Massachusetts? Northfield Mountain, where we looked at the top, it's connected to the Connecticut River. And it has the water down in the Connecticut River. It pumps it to the top of the reservoir, which is the top of the mountain. This is a picture of half of the units. So I think it's half. Let's see. Yes, it's half. I'll zoom in a little bit. There are 4 units there, and shown on this drawing are only 2 units. Here's unit number 1 and unit number 2. So there's 2 more units that's shown on a separate one-line diagram. So if I look at this, right, you can see that I have a rotary exciter. This is the DC generator. They actually have a slightly different design where they use a solid state. This is called, it's ABB. This is the excitation. But this is a synchronous machine. So when it's getting water from the top of the reservoir, they run water through the turbine, and they get the generator spinning when it's going there. But remember, they have to pump water up to the top of the mountain. So wouldn't I just use the generator / motor? See, it says both here, to go ahead and take the water from the river and pump it up to the top of the mountain. Why would I buy a separate motor? I can do that right here. The problem is this motor wants to run, what do we say, 257 RPM? And if you hit the switch, it would try to run at that speed instantaneously. So look closely over here. What does that say? That's a starting motor. That motor's job is to get this machine up and running close to whatever 257 RPM, whatever that works out to be, so that you can actually start to run it as a pump on your own. So here's an application where you can see all 4 units have the starting motor to go ahead and get it up to speed. All right, so anytime you want to start a synchronous motor, that's a big one, you have those options. You used to do something called damper winding. These are smaller ones. So most synchronous machines have damper windings to kind of smooth out operation. If they were built heavy duty enough, you could start it essentially as an induction machine. So that would be one option. And then the other option is you can actually short circuit the field. And that also kind of looks like an induction machine, and you might be able to start it up that way. You don't see these bottom 2 very often unless the motor is fairly small. Big ones, you really only have these 2 choices, an external prime mover or variable frequency drive. And if you think about the pumped hydro storage facility that was built in the 60s, did variable frequency drives exist? Not really, right? If you think about, if you look, you all are too young, but if you look back from the 70s, a big advertisement was transistorized radios, because it used to be tube amplifiers. And so they thought this is new technology. We wanted with transistor radios. So that's, they just didn't have the technology at the time because it was too new and too big. All right, let's take a look at example. Yes, sir. It's just, usually it's just a standard induction motor. So the motor is nothing fancy, but usually to couple it to the machine that you have to operate, that's where you have to run. You might be running at different speeds. So you might run through a gearbox that you have variable gears. Or the one that I worked in Houston had something called an overrunning clutch. So it actually would decouple itself and it would be able to do it that way. So some sort of a transmission, gearing type system would allow you to get up to speed. All right, so here's a simple example. 100 MVA, 12.5 kV, operates at 0.85 lagging power factor. Let's mix it up a little bit and let's call it a 50 hertz machine instead of 60. See what changes, if anything. 2-pole Y-connected synchronous motor, has the X sub S 1.1 and R sub A 0.012. What is the magnitude of the internal voltage at rated conditions, and what is its load angle at these conditions? So to do A, I have to start by drawing my circuit. So this is J 1.1. This is 0.012. My current is going in. My terminal voltage, we're going to assume it's operating at nominal 12.5 kV. Is that correct? We put it at an angle of 0. Is it 12.5 kV? Yeah, we're going to divide it by square root of 3 because it's a Y-connected machine. The 12.5 is across 2 phases. We have to do the single phase equivalent to be able to represent that. So we don't have 12.5 if it's Y-connected. We have 12.5 divided by the square root of 3. Now I'm going to calculate I, because this is unknown. So my current I'm going to be able to calculate it. Fortunately, I have that information. 100 MVA at a 0.85 lagging power factor. So S is equal to 100 MVA. And the angle there is the inverse cosine of 0.85. Is that a plus or a minus value? Is it plus 0.85 or minus? Minus? Well, who is lagging whom? The current lags the voltage, right? But when I do S equals VI conjugate, don't I get a positive theta? So this is going to be a positive number. So that's my value of S. And at 100 MVA, you know that's a three-phase machine. So I'm going to calculate I using S equals the square root of 3 VI conjugate. I'm using the square root of 3 because I can plug in 12.5 kV there. And I also see that this voltage, this current is the line current, but that also equals the phase current in a Y-connected machine. So I is going to be equal to S over the square root of 3 VL, and I take the conjugate of that angle. Okay? Make sense? Let's see. Everybody buying that? Going to run it through a MATLAB. So again, this is just a calculator. Here's my S, 100 mega at an angle of 0.85. Here's my terminal voltage. I combined my internal impedance all into one step. So 0.012 plus J 1.1. Calculate I, doing that conjugate of S divided by square root of 3 times V. Then I just display the current magnitude and angle. Now I'm actually going to go ahead and calculate what ET is. So ET equals a terminal voltage, or EF, sorry, equals a terminal voltage, or ETV, whatever it is. I should probably call it EF. I apologize. Hopefully it doesn't cause any confusion. But it's the internal voltage. It's going to be the terminal voltage. Notice to divide by the square root of 3, because I got to convert that to a single phase equivalent. And then I subtract the voltage drop across the internal impedance. Then I just display the magnitude and the angle. The item number 10, the angle associated with ET is the torque angle. Okay. So let's run that to here. And let's take a look at our MATLAB. So I get an internal voltage. This is the per phase equivalent of 6.21. And the torque angle is essentially minus 44. We could also, just for giggles, check and see that that machine that's operating at, what did we say? It was operating at 12.5 kVA, operating at a lagging power factor. You can see that it's only, its line voltage is about 10.8 kV. And we said when Q is going into the machine, the internal voltage, that internal armature voltage, should have a magnitude less than the terminal voltage, which this does. 12.5 is greater than 10.8. So sanity check of our number is correct. Yes, sir.
S is equal to 100, right?
100 MVA.
Why don't you divide it by 3?
I can. You can certainly divide it by 3, but by keeping this as a three-phase number over here, I can use this equation because these are all, I can get single phase quantities or phase quantities using this equation, right? Because we know I line and I phase are the same in a Y. So as long as I use this equation, it's fine. I could have divided it by 3, and that would be equal to V phase I phase conjugate. I could have used that one too. That would have been perfectly fine, but either one works. This equation is a lot more useful to us right here because we typically work with line quantities, so it's usually easier to use this equation. All right, the last thing is ignoring losses in the motor. What torque must be applied at full load? How would you calculate if we don't have any losses in the motor? What power or what torque must be applied? And this is the torque, meaning if you're dumping in 100 MVA at a 0.85 lagging power factor, how much induced torque on that machine must be? Otherwise, it's going to overspeed, right? You have too little torque, it'll continue to speed up. Well, power equals torque times omega. Omega, if you remember the equation, is equal to, what's the equation? It's 120 F over 2, but that's in actual RPM speed. And then I multiply that to convert that to from RPM to radians per second. I've got to multiply that by, I think it's pi over 30 to do the conversion. And that's how I get that value. So my power here, I know I'm inputting 0.85 times 100 MVA. So P in is 100 MVA times 0.85 or 85 megawatts. Omega, we have to do the calculation. So we have to do this calculation for a 2-pole machine to do the conversion over. And then my torque is equal to power divided by omega. I wanted to make this problem a little more challenging for myself. So I got rid of ignoring losses in the motor. How would you modify this problem? Do you see any losses in the motor that's shown up on the figures or on this slide? Don't I get I squared R losses there? So to actually calculate what the applied torque needs to be, or the mechanical torque, now I've got to go ahead and do a little bit of calculation. So I pulled out my load, and in MATLAB, I could have multiplied it by 0.85. Also in MATLAB, because I had this as a complex number, I'm just going to take the real part, because that's the same thing as the power. And then I subtract from it the loss. So P loss equals I squared R. That's the resistance loss. Keep in mind, this is the absolute value of I, not I itself. So the difference between my load, which is what I'm being electrically provided with, and the output is I just have to subtract the loss. And then this, I forgot to multiply that by pi divided by 30, which converts RPM to radians per second. And then my torque is here. So let's continue. Whoops. I might have to save it. It's giving me some agita, so let's save it. So this machine had better have a load of 270, give or take, kilo Newton meters of mechanical torque. Otherwise, the machine's going to overspeed. Okay. Questions on how to do that? Any questions?
The power E line.
P in, because electric power in, because it's a motor. It converts electrical power to mechanical power. That's what a motor does.
Yeah, so you said you use the 100, right?
100 MVA?
Times, the cosinus of the, the cosinus of the 100, right?
Or I can just multiply by the power factor, because the definition of power factor is P over S. So if I just take S and multiply by the power factor, I get P.
And then that's the feed is it in three phase or in four?
It's in three phase. Three phase.
So we're using the three phase or we're going into one for a single.
Yeah, that's a good question because the power going in is a three-phase power. Each one of those phases is contributing to the amount of torque output that the machine consumes or can supply. So you don't divide that by three because each one is adding torque. Yes, sir. Sure. Yep, I can do that. How about this one? Now I'm going to go to 60 hertz. Slightly different machine. So we have 120 MVA, again, Y-connected machine, 13.2 kV, operating at a 0.8 lagging power factor. Its synchronous reactance is 0.9. So the first thing I like to do is draw a circuit. This is J.9. This is 13.2 kV at an angle of 0, divided by the square root of 3. This is my current I going in that direction. It's operating as a motor. The power S is 120 MVA, and its angle is the cosine of 0.8. We already talked about a lagging power factor. That S should be a positive number because Q is going into the machine. So this is a positive number, and that is equal to S. So now we need to calculate what the voltage regulation is. So V no load minus V full load over V full load. So percent VR, V no load minus V full load over V full load times 100, right? So the first thing we need to do is calculate what this EA needs to be equal to, okay, to be able to have these conditions. So I can see that EA is going to be equal to my terminal voltage, the single phase equivalent, minus my current times J.9. The current we calculated before, we use S divided by the square root of 3 times V. This is the 13 equals 13.2 kV. This is the key thing. We've defined terminal voltage over here as a phase quantity. Over here, that should be a line quantity. So make sure you put 13.2 and not the square root of 3 divided by. If not, you have to change that from a square root of 3 to a 3. Once I have that, I'm going to have this EA voltage. Now, my no load voltage is when I goes to 0. Once I goes to 0, this voltage will actually be on the output of the machine. So the no load voltage is EA, and the full load voltage is VT. And those are my values. So I have a separate MATLAB script file for that. This one's a little easier. And again, nothing up my sleeves, clear CLC. Here's my load, 120 mega at an angle of whatever the inverse cosine of 0.8 is. Here's my terminal voltage. Here's my load. Conjugate of S divided by square root of 3 times VT, where VT is the original 13.2. I just display the current, magnitude, and angle if you're interested. Then I calculate the single phase EA. So VT divided by the square root of 3 minus the load through that into the generator or the motor times J.9, which is a synchronous reactance. And then my voltage regulation is my no load. Actually, I get this backwards. Should be my yeah, it should be backwards. Sorry about that. So it's the absolute value of EA minus, oop. Where's insert? Here we go. Divided by my terminal voltage, because the full load voltage is what the actual terminal voltage is going to be. I don't care about voltage regulation inside the machine because I can't access that. So I'm only interested in that value. So let's save and run it. And I get minus 6.67. So the voltage is going to drop. It's going to go down, not up. It drops a fair amount. So any questions on A? Because the other two questions are pretty simple questions, pretty simple answers. 'Cause I
Oh,
don't-
did you use the phase
Right.
voltages?
Did I use phase voltages?
Yeah, to find the percent VR.
Yes. So this is a single phase value, EA, and then if you notice my VT, I divide by the square root of 3. You can use line voltages, Drew, but the thing is, over here, I only calculated a phase voltage for EA. So if I want to use line voltage, I'd have to multiply the EA in this step by the square root of 3. So it's just, it doesn't matter. You can use phase or line voltages as long as they're consistent, the results will be the same.
All right, sounds good.
Okay. Nobody wants this MATLAB file, right? It's kind of simple and boring. Take it as a, we don't want it. It's fine. I don't have to post it. I just, like I said, MATLAB's a calculator for me. I just makes it simple. So I'll post this one here. And I won't bother with this one unless people want it. So what is the voltage and apparent power rating of the motor if it's operated at 50 hertz? With the same armature and field losses as it is at 60 hertz? It's going to be essentially the same. Basically the same. Because you're going to have to adjust your field current to maintain that same terminal voltage. So you can operate a 50 hertz or 60 hertz machine. You can operate them in either one. You just might have to drive more field current into the machine or less field current. Because remember, our internal voltage is dependent on K, machine constant, phi, which is equivalent to the magnetic field, and omega, which is the rotational speed. So if you're running at a lower speed, you're going to have to drive more field current into the machine to be able to produce that same voltage. So the voltage and apparent power rating should be the same, regardless of 50 or 60 hertz. Now, it may not necessarily work that way because a machine that's designed to run at 60 hertz is going to run faster than 50 hertz. So the cooling might be different. Okay. So that's a mechanical things that our mechanical engineering friends have to worry about. Let them figure out if it can operate and get enough cooling into it and running it at 50 hertz. We're just going to focus on the electrical characteristics. And as far as we're concerned, it should be fine. But mechanically, will it heat up? That's their problem. And the voltage regulation, it's probably going to be a little worse at 50 hertz because you don't have that same rotational speed. It's running at a slower speed, which means you're going to have to drive more field current in there to be able to get it to go. So just kind of responses there. Wow, this equation looks the same. The induced torque on a synchronous motor or generator, it's the same equation. 3 times V phase EA sine delta divided by omega M XS. And going back to Barzili's question about do you use single phase or 3 phase, you will notice the 3 out front of here. That's because this is an individual phase voltage, an individual phase voltage here, and that's just a phase impedance. So this would be the single phase. If you took the 3 out, that's how much one phase could produce for torque. But because we have the 3 out front, that's where we have all 3 phases. We derived it last semester. I mean, last chapter, where you had to look at, it was basically where we multiplied the V and the I. Remember, we did the S equals VI, and then we multiplied the real parts and the imaginary parts. This is the term that we ended up with. So again, that really is the best way to have some impact on the change on a sort of a steady state basis. But monkeying with delta, increasing or decreasing the torque angle, is how you can get more power out of the machine. And here's a phasor diagram, just kind of summarizing what we talked about. The more lagging a power factor, right? The more, I'm sorry, I'm not lagging, the more leading a power factor. So this is unity. And if we look, our AEA2 is unity here. We can see that this is this value, but then we can adjust it and we can get a slightly different value. Actually, I think I have these, let's see. This should be, oh no, this is correct, yeah. So this is a lagging power factor, I mean, a leading power factor, which means we're dumping some reactive power out of the system, out into the system. This one is unity when we're not doing anything, and so you can see the impacts on the phasor diagram. V curves only exist if you're actually using your synchronous machine as a motor. And these are a lot more useful than looking at phasor diagrams because it tells you what armature current you can produce, what field current you need based on different values of power out. So if you have more applied torque, you increase or decrease. And you can see if my power factor is unity, if I go in this direction, I'm putting in more excitation current. So this region here defines if I'm overexcited or if I'm underexcited. That's the difference between the two. And these actually show as I increase the field current, my armature current drops until the lowest value of armature current I can have is when I actually am at unity. And then my as I increase my current, now I'm starting to export power. So I'm dumping out reactive power into the grid. So the current has to go up because I'm now supporting power to the grid. Over here, or reactive power to the grid. Same thing happens with a lagging power factor because now my armature current has to include any reactive power inside the machine. So that current value has to increase. So that's why it bottoms out at unity power factor, because all I'm providing, all the armature current is providing at that point is the power to rotate the machine. So any friction and windage losses, plus whatever applied torque is. All the internal power that is needed for the field, that's being taken care of by the machine. So that's when this current value is going to be the least. And this is just a plot, but if I look here, this is that Northfield Mountain. This is the same thing. These are the generator V curves, and you can see overexcited on the other side of this minimum point where my power factor is at unity, and underexcited where I can see that it goes back up. And then you'll notice these are different ratios. So if you look here, this is no power. So if you're not putting any power in, which isn't realistic, but you're not pumping at all, you're basically just doing friction and windage, you can see what you have over here. Now I start increasing the amount of power demanded. Or this is, sorry, this is the power factor you follow here. And then these curves right here, the blue lines. So the blue one is the 0. Then we go to 0.5, 0.6. And I guess they didn't want to show. Oh, sorry, I'm looking at the wrong part. This one, it actually doesn't even show what the blue one are, the blue curves are. You have to read it off there over here. You can see it says 25 MVA, or 25%, 50%, 75%, and 100%. So each of these blue curves tell you how much power that machine is drawn as a percentage. So 25, 50, 75, 100, and these lines all indicate what the power factors will be. So again, trying to show real world that this is the actual V curve for those generators at Northfield Mountain. Okay, that's all we're going to cover for synchronous motors because they're basically the same as synchronous generators. Everything that we've studied is applicable. It's just the direction for current goes in or out, and you get the values there. So questions? All right. I will see you on Thursday. Have a great day, everyone. We'll see you
Hey,
then.
Paul.
Take care.
You too, Paul.
Thank you.
Paul, can I ask you a quick question on the homework?
The homework, sure.
All right. So I was working on part 2, and it was part B that was quite confusing.
Problem number
Finding
two. Homework
finding
number.
the field current
Is this homework number
Required.
4?
Believe so.
So part B of problem number 2, yeah.
Yeah. Do you
Okay.
end up using that graph at all?
Yes. So what you need to do is you need, because this right here, that's the open circuit voltage. I need to calculate what the actual internal voltage needs to be to deliver this power here, 480 at 1,000 amps at a 0.8 power factor. So once I know what the voltage is, say it's something over here, right? Or I'm sorry, on this curve. So then at that point, I can actually look and see, oh, I need 4 amps of field current to be able to deliver, 450 volts, or I need 8 amps of field current to be able to deliver that. So you've got to get what your EA needs to be to calculate what that voltage is going to be, or the field current is going to be. Does that make sense?
Okay. Oh, okay. Yeah, that does make sense.
Yeah, just remember when you're doing this, you need to calculate what this voltage needs to be here to deliver 480 at 1,000 amps at a 0.8 power factor. So you need this voltage drop. Once you know what EA is, let's say it's here, you read it off the curve, and then you drop down, and that tells you what your field current needs to be.
All right. If you're drawing on something, I can't see your screen right now.
Oh, sorry.
too.
I thought
There
I
you
was showing my screen, so bear with me. Is that better?
Yeah. So you still use that open curve. Okay.
Yep, you still use the open circuit characteristic. That's the only way to measure. So
Yeah.
that's gonna give you a field current to drive that. So
Okay.
the internal voltage will be, whatever it needs to be able to provide that. So clearly, this is the open circuit voltage. This is what EA is going to be. But the reality of it is the actual terminal voltage, what you can measure, will be further down here.
Okay. I guess I was just confused because on the graph it has open circuit terminal voltage, and then it also says
Well, isn't the open circuit terminal voltage the same thing as EA when there's no load connected? The drop
Okay.
here would be 0 volts.
so the difference with a load is that you have that, or when
Yeah,
it's not.
so this would be what EA is, because EA is just K phi omega, but the
Yeah.
actual terminal voltage will be something else over here.
Right. Okay.
Okay.
Yep, that makes sense.
All right, if you have more questions, I'll be in my office in a few minutes. You can ask that, okay?
All right, sounds good. Thank you
All right.
very much.
All right, take care,
Thank
everyone.
you, Paul.
Thank you.
Yes.